All right. Good afternoon. Um, Once again, just going back to what we have been dealing with in the case working with uh, functions and most recently operations between functions. And we have, it's kind of going back, okay, so we have concerning operations between functions. And we have on page 225, okay, and we have a trio of functions. And for what we have in the mix, okay, so we have functions, okay, assigned, okay, where we have f of x is equal to x cubed minus 4x. And we have g of x, okay, is equal to the square root of 2x. And we have, okay, h of x is equal to 2x plus 3. And we have, in the case working with the composition of functions, and we have for number 47, again on page 225, okay, we're now looking at f composed with g of x, okay, whereupon we have x is set equal to 8. All right, so this is the compositional notation, and just for what we have, putting the composition exclusively in functional notation. So this will come out to, in the rewrite, we have f of g of 8. So you have f of g of 8. Now the output function we're going to have at f. And just to kind of give you a little bit of a segue here. Okay, so operating in accordance with f. And again, we're going to have f of the input is going to be equal to the cube of the input minus 4 times the input. Okay, now the input right now we have at g of 8. And so in terms of g of 8, okay, so you can either go ahead and get the value of g of 8, or you can just do it, sort of in midstream. Okay, so we have okay, so you got the cube of x minus 4 times x if x is the input. Now with g of 8 as the input, okay, so we're looking at the cube of g of 8 and we have minus 4 times g of 8. And looking at what we have numerically, okay, for g of 8. Now g of 8, we're going to derive this value, okay, from what we have in g of x. So if x is at 8, okay, so we're going to have for g of 8, we're going to have the square root of 2 times 8. And 2 times 8 is 16. And the square root of 16 is equal to 4. Okay, so in translating what we have here, so for g of 8 cubed, okay, so we have the cube of 4 minus 4, okay, and we have times g of 8, again, which is going to be at 4. And 4 cubed is 64. Minus 4 times 4, so this would be minus 16. And 64 minus 16 comes out to 48. All right. Now, with the same set of functions given, okay, and we have with number 48, and we have with the next composition, okay, now we have h of g of 2. Okay, so the layout we have h composed with g of 2. And so we have with g of 2 as the input. Okay, now we're operating in accordance where the output operation, okay, is h. So again, we have h for any input is going to be equal to 2 times the input plus 3. Now we have with g of 2 is the input. Now we have 2 times g of 2 followed by the addition of 3. And for what we have numerically, okay, so again, before we looked for g of 8. Now in this problem we were looking for g of 2. And operating in line with g of x. So g of 2 we have equal to the square root of 2 times 2. And 2 times 2 is 4. And the square root of 4 is equal to 2. Okay, so we have filling in. Okay, so we have 2 times 2 followed by the addition of 3. 2 times 2 is 4, and 4 plus 3 is 7. All right, now in the next phase, okay, so we still have continuing, okay, with our functions f of x, g of x, and h of x as they are assigned. And for what we have in the case of number 48, now we have h composed with f whenever x is set equal to 1. Okay, so we have with number 49, okay, so we have, we're looking at h composed with f of 1. Okay, so we have h of f of 1. Okay, so we have, once again, we have the output function is at h. So again, we'll operate in accordance with h of x. Again, have h of the input is equal to 2 times the input plus 3. Now we have, instead of x, we have the input at f of 1. And looking for the numerical value of f of 1. So we're going to attain f of 1 upon utilizing setting 1 for x, for f of x is equal to x cubed minus 4x. So here we're going to have 1 cubed minus 4 times 1. 1 cubed is 1, and we have minus 4, and 1 minus 4, okay, we have equal to negative 3. And for what we have in following through, so 2 times f of 1, we have f of 1 at negative 3. And we have in terms of the follow through, okay, so you have 2 times negative 3 is negative 6. And we have for negative 6 plus 3, okay, so we come out to minus 3. Now, for what we have for the next composition problem, okay, so we have with number 50. And here we have g composed with f, whereupon x is set equal to 3. All right, so you have g of f of 3. Okay, and so we have in this layout, okay, we have the output function to be at g. Okay, so in terms of the treatment of f of 3, okay, so g of the input we have by design is equal to the square root of 2 times whatever input there is. And so for g of f of 3, okay, we have the square root of 2 times f of 3. And for the evaluation of f of 3, again, deriving from f of x, so f of 3, okay, so we're going to have f of 3, so you have x cubed, so this will be 3 cubed minus 4 times 3. 3 cubed is 27. We have minus 12, and 27 minus 12 comes out to 15. Okay, so with f of 3 at 15, we're going to have in the follow through. Okay, so you have the square root of 2 times 15 and in this particular case would come out to the square root of 30. Okay, and since 30 is an even number, I can understand why one would expect this radical to be reducible, but it turns out that out of the perfect squares, 1, 4, 9, 16, 25, 36, and so on, that the highest perfect square divisible into 30 is only 1. So the square root of 30 in the exact form, that is already in simplest form. And now, for what we have, okay, still working with the same set of functions, and we have, again, still working with fg and h of x, okay, with the same expressions, and we have for number 52, and this time we have for this problem, so we have h composed with f of -1 Okay, so you got f of -1, that is our input function. And now the output function, okay, again we have, once again we have h as the output. And so just creating the pattern in terms of the follow through with the development of the compositional result. So we have h of the input is equal to 2 times the input plus 3. And in the composition, now we have 2 times f of -1 followed by the addition of 3. And again, just for the specific value of f of -1, okay, so for f of -1, so we're looking at the cube of -1, and we have minus 4 times -1. So you have -1 cubed is minus 1. -4 times -1, this will be a plus 4. And -1 plus 4 is equal to 3. Okay, so just carrying over to what we have for the composition, where we have f composed with f of -1. So we have 2 times 3. Followed by the addition of 3. So we have 2 times 3 is 6. And 6 plus 3 is equal to 9. Alright, now for what we have in the next set of items, okay, and we have concerning compositions, okay, and we have from number 53, okay, so this time we have a composition between g and f, where we have g composed with f of x whenever x is set equal to 5. Okay, so you have g composed with f of 5. And this is where we have g of f of 5. Okay, and again, so we have with the output function in this one case, we have at g, and again, we had the input at f of 5. Okay, and so in terms of how f of 5 is going to be treated, again, in accordance with what we have for g of x, g of the input is equal to the square root of 2 times the input. Okay, so you have 2 times f of 5 inside the radical. And so for f of 5, okay, so with x at 5, so we have 5 cubed minus 4 times 5. So you have 125 minus 20. And so this will come out to 105. Okay, and so just transferring that over back into the radical. So we have the square root of 2 times 105. And this will come out to the square root of 210. Okay, and this is going to be a little bit of a surprise too, because with 210 is a high even number, one would think that there would be a perfect square that is higher than 1, but believe it or not, all the other perfect squares, 4, 9, 16, 25, 36, and so on, will not go completely into 210. And in fact, the square root of 210, okay, that is going to be in simplest radical form. And here, okay, we have, for the next group, okay, so we have m of x is equal to the square root of x plus 8. And we have with n of x, for n of x, okay, n of x we have equal to x minus 5. And then we have p of x, and p of x, okay, we have equal to x squared minus 9x. And we have a q of x, I have equal to 1 over x minus 10. Okay, now for what we have in the case of the compositions here, okay, and we have with number 65, okay, now we're looking at n composed with p of x. Okay, and so that's going to be equal to n of p of x. Okay, and just, okay, so your output function, again, you have n of x equal to x minus 5. Okay, so again, n of the input is equal to the input minus 5. Okay, so if the input is at p of x, we're going to have n of p of x is going to be equal to p of x minus 5. Okay, so if we pause just a moment, okay, so you have the composition going to the functional notation, and again, output function you have at n of the input is equal to the input minus 5. And we have the input at p of x. So p of x takes the place of x. So you have p of x minus 5. And then following through with the variable expression. So we got p of x at x squared minus 9x. And we have followed by the subtraction of 5. And so we're going to have for the end result here, it's come out to x squared minus 9x minus 5. Okay, so this is going to be the composition here. Now, in the case of the domain of compositions. Okay, again, there are two criteria. Okay, again, we have with the input function, we have the input function. Okay, so you have that p of x is equal to x squared minus 9x. Okay, so we don't have an even root radical, and we do not have a fraction. So that part has no restriction. Now as for what we have in the output, for x squared minus 9x minus 5. You notice, okay, we don't have a fraction, we don't have an even root radical for x, and x could be anything 0, positive, or negative. Okay, and just like the input, there is no restriction. So that means that for what we have between the input and the output, okay, that means we're going to have no restriction at all. And because there's no restriction to combine between the input and the output, that means that for this composition, if there's no restricted value, that means that the value of x can be anything in the real number system. So we have for the domain, we're going to have the set of all real numbers. Right. Now, in the case of the next composition, okay, and this is what we have in number 66, and this time we are involving, okay, the functions p and n. Okay, and so just taking what we have, oops, okay, so for 66, again, going back to the same set of functions. Okay, so I have p composed with n of x. Okay, and just putting in compact functional notation. Okay, so p composed with n of x. So we have p of n of x. All right, so in this layout, okay, now if you notice, okay, in 65, the output function was n of x. Now in number 66, now we have the output function is going to be p. And guess what? P of x is equal to x squared minus 9x. Okay, now this time again, so you have the input is going to be at n of x. So again, what I'm going to do with n of x, I'm going to square it. And have also minus 9 times n of x. Okay, and just taking what we have in the variable expression until I'm just going to work down here. So you got the square of n of x. What is n of x? Okay, that is given as x minus 5. Now we have minus 9 times n of x. So you have minus 9 times all of x minus 5. And for the square of x minus 5, so I have x squared minus 10x and I have plus 25. And distributing negative 9 over the quantity of x minus 5. So we have a negative 9x plus 45. And joining together like terms, so I have x squared, negative 10x, and a negative 9x will form negative 19x. And 25 and 45, okay, that will make 70. Okay, so that will be the resulting composition on this one. Now, in terms of what we have regarding the domain, okay, so again, n of x is going to be your input function. Okay, so n of x equal to x minus 5. Again, there's no fraction or even root radical. So you have no restriction. And again, we have with the output, that is the composition itself. So you have x squared minus 19x plus 70. Again, you don't have a fraction or an even root radical. Also, no restriction. And so between the input and the output, between the two, okay, you have no restriction at all for the composition. And once again, we're going to have for the domain of the composition, okay, we're going to have the set of all real numbers. All right. Now, in the case of what we have in a little bit of a change up, okay, so we've been looking at the functions n and p. Now, looking at starting to pair up with what we have among the quartet of functions. Okay, and we have for 67, we're now utilizing the function m. And for 67, so we have m composed with n of x. And again, just putting in compact notation. Okay, so I have m of n of x. Okay. All right. So this time your output function is going to be m. So you have a different operative here. Say m, whatever the input is equal to the square root of the input plus 8. And for m of n of x, so we have the square root. Okay, so n of x is going to represent x. Now, I'm going to replace n of x to its variable expression equivalent. Okay, so I have n of x, again we have x minus 5. And x minus 5 followed by the addition of 8. We're going to have for this resulting composition, okay, this is going to be the square root of x plus 3. Okay. And regarding the input and the output, so again, n of x is the input. Okay, so we have n of x equal to x minus 5. And again, since we have a direct expression, no fraction, no even root radical, again, you have no restriction upon the input. However, for the output, we have the square root of x plus 3 and because they have a square root, again, whatever is inside the radical cannot be negative. Okay, so x plus 3 can be 0 and it can be positive. Okay, so if x plus 3 is greater than or equal to 0, and if I take 3 away from both sides, so I have that x is greater than or equal to negative 3. Okay, so for what I have regarding the input has no restriction. And we have regarding the output, okay, it has the restriction that x is greater than or equal to negative 3. So for the whole composition, okay, the restrictions we have come under the circumstances solely from the output. So we have that x is greater than or equal to negative 3. And so we're not going to have the domain of this composition to end up as a set of all real numbers. Instead, it's going to be those values of x greater than or equal to negative 3. And just for the interval notation, so we're starting from and including negative 3. And negative 3 is going to be in the bracket thanks to the equal sign. And we have going up and out toward positive infinity. All right, now for what we have in the case of the next composition, so we have a little reversal of the order, and this is where we have n composed with m of x. So we're still involving the same two functions, but again you have a switch in the order. Okay, notice we had in 67 we had m composed with n of x, we had m of n of x. Now we have the switch around where we now have n of m of x. So your output function is now going to be not m of x but n of x. So you have in this one. Okay, so for n of x, okay, we're going to have equal to x minus 5. And for n of m of x, okay, so m of x takes the place of x. Okay, so I have m of x minus 5. Okay, and in place of m of x, again, we had the variable expression. So we have the square root of x plus 8, followed by the subtraction of 5. Okay, and here we have, for this difference, okay, that is going to be the final composition. And where the domain comes in. Okay, so you have the input. Okay, so you have m of x is equal to the square root of x plus 8. And again, because they have a square root, x plus 8 cannot be negative. And we have the x plus 8. It can be 0 and it can be positive. Okay, so we have the x is greater than or equal to negative 8. Okay. And just a moment. Okay, so we have for the output, we have the square root of x plus 8 followed by the subtraction of 5, and we're going to have the same kind of restriction, and restriction on x is going to keep x plus 8 from being negative. So we're still going to have that x is greater than or equal to negative 8. So between the input and the output, okay, we have only one restriction, and it happens to be shared between the input and the output. So we have the x is greater than or equal to negative 8. And so we're going to have, in the case of the domain, so we're going to go from and including negative 8, all the way out to approaching infinity. No, and the reason for this is that if you go by the formula, okay, you have minus 5 is detached from the input. Yeah, so m of x is going to be the input, okay, and the minus 5 is separate from it. So m of x, you have the square root of x plus 8, and the minus 5, that is not going to be pushed under. Okay, so m of x is its own term, minus 5 is going to be detached. Yeah, so you're going to keep those terms apart. Yeah, so you're going to keep the square root of x plus 8 as the square root of x plus 8, and the minus 5 is going to be minus 5, and you cannot combine these terms together. Now, in the case of what we have, okay, still with the same functions, and we have a couple more items, and we have with the compositions, okay, in 70 and 76. Okay, so we have with 70. Okay, so we're looking at working with now. Okay, so this is going to be our first appearance of Q. So we have Q composed with P of X. Again, so we have Q, P of X. Okay, so your output function is now going to be, at Q. And in terms of how to operate in accordance with Q, so you have Q, the input is going to be equal to 1 over the input minus 10 so we're going to have 1 over P of X minus 10. Okay, so again, P of X represents X. And for P of X, okay, so you have X squared minus 9X. I'm just going to add parentheses just to emphasize that X squared minus 9X refers to P of X. Okay, so we have for the resulting composition, Okay, we're going to have 1 over x squared minus 9x minus 10. Okay. And where the domains will come in. Okay, so we have with the input, so again, p of x we have equal to x squared minus 9x. Okay, and again, x squared minus 9x, you do not have a fraction, you don't have an even root radical, so this one has no restrictions. Okay, now on the other hand, we have with the output, okay, we have 1 over x squared minus 9x minus 10. And because we have the variable expression in the denominator, okay, we cannot have the bottom part of the fraction equal to 0. So we have, looking at factoring, okay, so x squared goes to x and x. Factors of negative 10, that will add up to negative 9. We'll have a plus 1 and a minus 10. And from these, okay, so if the expression cannot be 0, then neither can its factors. So from x plus 1 not allowed to equal 0, we have the x cannot be negative 1. And for x minus 10, if this cannot be 0, then we have the x cannot be equal to 10. And so just looking at what we have with the input, as well as what we have from the outcomes restrictions. Okay, so we're going to have the restrictions in this case will come from the condition in the output. Okay, so we have the x cannot be negative 1 or positive 10. And just to give you a little bit of a visual, so you have two values that are left out. Okay, so you have a negative 1 and positive 10. So negative 1 is left out, 10 is going to be left out. And just for the activity around these values, okay, so we have values of x that will be less than negative 1. You have those values of x between negative 1 and 10, but not including either of these values. And then we're going to have those values of x that will be greater than 10. Alright, so we have for the domain, okay, we have two exclusions from the domain, from which if I display an interval notation, okay, we're going to have three separate sections, and from the lowest end, I'm going to have those values less than negative 1. And then we have those values between but not including negative 1 and 10. So I still maintain the use of parentheses. And then we have for what we have at the upper end, okay, we have those values of x which will be greater than 10. And again, we have parentheses around 10 and infinity. All right, now in the case of 76, all right, And in this one case, so we're looking at just one function involved. And this is what we have with P composed with itself of X. Okay, so we have P of X. Now, again, so the output function, okay, we have P of X, so P of whatever the input is, okay, we have equal to X squared minus 9X. Okay, now, this is where it gets a little bit tricky because you have a bit of repetition here, but remember, P of the input is equal to the square of the input minus 9X. Well, guess what? The input happens to be P of X. So just kind of following through. So P of X replaces X. Okay, so you have the square of P of X minus 9 times P of X. And so I'm just going to work down here. So P of X is X squared minus 9X. And that's going to be squared now from minus 9 times P of X. So you have minus 9 times all of X squared minus 9X. And for the square of X squared minus 9X, so you have X squared minus 9X times itself. So we have X to the fourth, and then we have for the outside and inside products, okay, those are each going to be at negative 9X cubed. And the last product, negative 9X times itself, that's going to be a positive 81X squared. And then we have with the other distribution, so we'll have negative 9X squared plus 81X. And putting what we have all together, so you have X to the fourth, and then we have minus 18X cubed. Then we have 81 minus 9, so we have a plus 72X squared. And finally we have plus 81X. Okay, so that's going to be our final composition. Now, again, we have with the input, so yeah, P of X is equal to X squared minus 9X. Okay, so you have no restrictions. And we have with the output, okay, so again you had this fourth order expression, and if you notice among the terms, okay, there's no fraction or even root radical among them. And this one has no restriction, so between the input and the output, okay, there's no restriction at all. And because there's no restriction for the input function and the resulting composition, this means that for the domain of P composed with itself, we're going to have the set of all real numbers. And that is going to be the resulting domain once again. All right. Now, in the case of what we have, and not so much dealing with, let's see. Well, there's a little issue with Alex, And I just want to mention, and this will be in the case of what we have with some of the reflections, and also working with items, such as odd and even functions. So just going to kind of give a little bit of a mini lesson on this one. Now, okay, now for odd and even functions. Okay, now an odd function. Now in terms of graphing, okay, now an odd function is going to be a function that is reflected about the origin. Again, origin being where the x and the y values are 0. And you have this to be defined by whereupon we have that f of negative x is equal to the opposite sign of f of x. So what this means is that for odd functions, then we have opposite sign inputs. Notice you have negative x and x. And notice the outputs, you have positive and a negative. Positive on the left, negative on the right. So for odd functions, opposite sign inputs are going to lead to opposite sign outputs. And we could take just as an example, okay. So let's see if I can get this one to show up. Maybe kind of show you using Desmos. So just give you a case of an example of an odd function. Okay, we'll say we have something like y is equal to x to the third. Let's say we have x to the third plus x. Yeah, we'll say we have, let me change that up a little bit. So you have x cubed plus, we'll say x cubed plus 2x. Okay, and just for key points here, so I'm going to put in a table. And again, I had mentioned that opposite sign inputs lead to opposite sign outputs. Okay, so you got the origin. And let's say that if I have, so I got -1, -3. And I got 1, 3. Let's say I have -2, -12. And notice I have +2, 12. I'll just take this out once more. Okay, so you got -3, -33, and 3, +33. Okay, and if you notice, okay, you're going to have both halves to be reflecting about the origin. Notice you have kind of going slowly to the right and then shifting up rather drastically. But across the origin, you have kind of shifting slowly to the left and then descending rather drastically. And notice we have opposite sign inputs, and the outputs happen to be opposite signs as well. -1, -3, +1, +3, -2, -12, 2, 12, and then we have -3, -33, and we have 3, 33. So this is a sample, like x cubed plus 2x would be an example of what we have with an odd function. Okay, now for what we have in the case of even functions. Now an even function, okay, that is going to be a function that is going to be reflected about the y-axis. And this one is going to be defined by the relation, okay. And okay, so we have defined by, okay, so we have f of -x. And this is going to be where we have equal to f of x. And what this is going to signify is that for even functions, we have opposite sign inputs. Are going to lead to the same outputs. And I'll give you just an example and also a bit of a visual. So I say we have something like f of x is equal to, let's say we have x squared minus 2. Okay, so if I change this function, okay, so we have x squared minus 2. And I'll just zoom in here. Okay, if you notice, okay, we have opposite sign inputs, and you end up with the same output. Okay, notice you have both of these halves are going to be reflecting about the y-axis. Okay, so you got on the y-axis, okay, you have the y-intercept is 0, -2, but along both halves for this parabola, they're going to be at the same level across the y-axis. Okay, so you have 1, -1, -1, -1. Got 2, 2, -2, 2. Then you had the opposite sign inputs at 3 and -3, and guess what? You got the same output or same y value. Both of these, which we end up at 7. So x squared minus 2, or y is equal to x squared minus 2. That is going to be a case of what we have with an even function. And again, so both halves reflect each other about the y-axis. Whereas with the odd function, you're going to have reflecting about the origin. Okay, so that is from a visual standpoint, okay, this is what we're going to have as the key differences here. All right, now, and just like in terms of identifying, let's say without graphing whether a function is odd, even, or none of the above, and we'll say that for instance. And you try this again. Okay, and we'll take just kind of use some building blocks here. Okay, so we have in the first case, all right, so we have, let's say we have just plain f of x is equal to x to the third. Okay, so we have with our function case, you have f of x is equal to x cubed and you have for an f of negative x. Okay, so if I operate with negative x in accordance with f of x is equal to the cube of x, you have f of the input is equal to the cube of the input. Now if the input is at negative x, okay, so I have the cube of negative x. Again, you have negative x times itself is positive x squared, and then in turn positive x squared times negative x is going to be a negative x cubed. Okay, and just for x and negative x, okay, so we're starting out with opposite sign inputs. And in the case of the outputs, notice we have a positive x cubed here and a negative x cubed over here. Okay, so these are opposite. Okay, and for what we have here, okay, opposite sign inputs lead to opposite sign outputs, and since we have unanimously opposite sign inputs lead to opposite sign outputs, this means that for what we have in consequence, okay, this is going to be an odd function. And let's say if I have, say like for f of x, if I have equal to x to the fourth plus 3x squared okay, so you have f of x, okay, so you have x to the fourth plus 3x squared. Okay, so if I had the input at negative x, so I have like negative x to the fourth, and I have 3 times, okay, what's going to be the square root of negative x? And guess what? We have negative x to the fourth. Okay, this will come out to positive x to the fourth and square root of negative x comes out to x squared, so we have x to the fourth plus 3x squared. Okay. And so for what we have at the start, okay, now the inputs are opposite sign, and now for x to the fourth plus 3x squared, okay, notice they have between the terms here, okay, so x to the fourth is the same, 3x squared, okay, had the same appearance, okay, and for what we have here for even functions, okay, opposite sign inputs lead to the same outputs, and so we have the same throughout, and so opposite sign inputs, you had the same expression in the outputs. So this is going to be a case of what we have with an even function. I'll show you a case here. If I have, let's say, f of x is equal to, let's say we have 3x to the fifth plus 7. So f of x equal to 3x to the fifth plus 7. Now for f of negative x, so we have 3 times the fifth order of negative x, followed by the addition of 7. Guess what? Negative x to the fifth, that's going to be minus x to the fifth multiplying 3. So we have negative 3x to the fifth plus 7. And looking at how this is going to compare with what we have given for f of x. Okay, so we have, again, the inputs are opposite. And if you notice, you have 3x to the fifth minus 3x to the fifth. Those are opposite signs. But if you notice, okay, we have with 7 and 7, those happen to be the same. And for what we have in the layout, okay, if the function is to be odd, you're starting out with opposite sign inputs, and the output must be opposite sign. If you have even at opposite sign inputs, the outputs must be identical. But if you have a scrambling, we have, part of the term and the output happen to be opposite and some happen to be the same, you're not going to have the function to be odd or even. So in this case, you have neither odd nor even. And it's because you have opposite for one output and then you have a term to be the same for the other. Say we have for this remaining case, if I have something like f of x is equal to x to the fourth plus 3x squared, and say we have minus 1. Right, having to apply this to the input at negative x. Okay, so running it through, so you have what's going to be the fourth order of negative x. And we have plus 3 times, okay, the square of negative x. And we have minus 1. So again, even power of a negative comes out to a positive. So you have positive x to the fourth. And we have negative x squared is going to be positive x squared and multiplied by 3. So we have plus 3x squared we have minus 1. So just looking at how the terms are going to line up. So again, the inputs are opposites. But for what we have, so we have x to the 4th plus 3x squared minus 1, or f of x, f of negative x, we have x to the 4th plus 3x squared, and also minus 1. So these are going to be the same throughout. And again, if you have opposite sign inputs leading to the same outputs, that's going to define an even function. Okay, so we have for this last case, f of x equals x to the 4th plus 3x squared minus 1. That's going to turn out to be an even function.